Flexible Metal Conduit, or FMC, has length restrictions defined by the National Electrical Code, or NEC. Specifically, NEC Section 350.30. A1 states that FMC should not be used as a raceway for more than 6 feet, which is 1.83 meters, unless it is continuously supported and protected against physical damage. Metal-Clad Cable, or MC cable, on the other hand, has different requirements. NEC Section 330.10. 8.1 specifies that MC cable should not be used as a substitute for FMC or liquid-tight flexible metal conduit where continuous mechanical protection is required. The primary reason for the 6-foot length restriction on FMC is its lack of inherent mechanical strength. FMC is flexible, which is advantageous in many applications, but it is not as structurally rigid as MC cable. In longer lengths, FMC can sag or buckle, potentially exposing the conductors within to physical damage. This vulnerability necessitates the 6-foot limit unless adequate support and protection are provided. MC cable differs significantly in its construction. It features a metal armor that provides continuous mechanical protection to the conductors. This armor is designed to withstand physical stress and impacts, thereby safeguarding the conductors even when the cable is installed in longer lengths. Consequently, there is no specific length restriction on the use of MC cable, as its design inherently offers the necessary protection. While both FMC and MC cable serve the purpose of raceways for electrical conductors, their mechanical properties differ substantially. FMC flexibility comes at the expense of structural rigidity, necessitating the 6-foot length restriction to ensure safety. MC cable, with its robust metal armor, offers superior mechanical protection, allowing for longer runs without compromising safety. Therefore, the NEC imposes a length restriction on FMC due to its lower mechanical strength compared to MC cable. The metal armor of MC cable provides inherent protection, eliminating the need for a similar length restriction. This distinction is crucial for ensuring the safety and reliability of electrical installations. It's important to consult the NEC and local codes for specific requirements and interpretations related to FMC and MC cable installations. These codes are updated periodically to reflect advancements in technology and safety standards. Here are some further considerations regarding the use of FMC and MC cable. Firstly, consider the specific application. In situations where flexibility is paramount and the length required is short, FMC may be suitable, provided it is properly supported and protected. Secondly, if the installation requires longer runs or greater mechanical protection, MC cable is the more appropriate choice. Thirdly, examine the environmental conditions. In areas where the cable may be exposed to physical damage, MC cable offers superior protection. Fourthly, review local electrical codes. Local jurisdictions may have specific requirements or restrictions on the use of FMC and MC cable. Fifthly, ensure proper grounding. Both FMC and MC cable must be properly grounded to ensure electrical safety. Sixthly, use appropriate connectors. The connectors used with FMC and MC cable must be listed for the specific application and cable type. Seventhly, avoid overbending. Overbending FMC or MC cable can damage the conductors and compromise the integrity of the installation. Eighthly, protect against corrosion. In corrosive environments, use corrosion-resistant FMC or MC cable and fittings. Ninthly, inspect regularly. Regularly inspect FMC and MC cable installations for signs of damage or wear. Tenthly, replace damaged cable. Replace any damaged FMC or MC cable immediately to prevent electrical hazards. Furthermore, understanding the ampacity of conductors within FMC and MC cable is essential. Ampacity refers to the maximum current, measured in amps, that a conductor can carry continuously without exceeding its temperature rating. The NEC provides tables, such as NEC Table 310.15, B16, that specify the ampacity of conductors based on their size, insulation type, and the ambient temperature. When installing conductors in FMC or MC cable, it is crucial to select the appropriate conductor size to handle the anticipated load. Overloaded conductors can overheat, leading to insulation damage, reduced lifespan, and potentially fire hazards. Factors that affect conductor ampacity include firstly, the conductor size. Larger conductors have a greater surface area for heat dissipation and therefore can carry more current. Secondly, the insulation type. Different insulation materials have different temperature ratings, which affect the ampacity of the conductor. Thirdly, the ambient temperature. Higher ambient temperatures reduce the ampacity of conductors, as they have less capacity to dissipate heat. Fourthly, the number of conductors in a raceway. When multiple conductors are installed in the same raceway, such as FMC or MC cable, their ampacity must be directed to account for the increased heat generated. Fifthly, the length of the run. Long conductor runs can experience voltage drop, which can affect the performance of connected equipment. Sixthly, the type of load. Continuous loads, which operate for 3 hours or more, require conductors to be sized at 125% of the load current. Seventhly, the terminal temperature rating. The terminals of connected equipment have temperature ratings that must be considered when selecting conductors. Eighthly, the presence of harmonics. Harmonic currents can increase the heating of conductors and require diode. Ninthly, the type of raceway. The type of raceway, such as FMC or MC cable, can affect the ampacity of conductors due to differences in heat dissipation. Tenthly, the grounding method. Proper grounding is essential for electrical safety and can also affect the performance of conductors. Additionally, consider the voltage drop in electrical circuits. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction, reduce lighting brightness, and increase energy consumption. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To minimize voltage drop, firstly, use larger conductors. Larger conductors have lower resistance and therefore experience less voltage drop. Secondly, shorten the conductor run. Shorter conductor runs have less resistance and therefore experience less voltage drop. Thirdly, increase the voltage. Higher voltage systems experience less voltage drop for the same amount of power delivered. Fourthly, use parallel conductors. Parallel conductors reduce the overall resistance of the circuit and therefore reduce voltage drop. Fifthly, improve the power factor. Improving the power factor of the load can reduce the current required and therefore reduce voltage drop. Sixthly, use voltage drop calculators. Voltage drop calculators can help determine the appropriate conductor size for a given application. Seventhly, consider the starting current of motors. Motors draw a high inrush current when starting, which can cause a significant voltage drop. Eighthly, use buck-boost transformers. Buck-boost transformers can be used to compensate for voltage drop in long conductor runs. Ninthly, use automatic voltage regulators. Automatic voltage regulators can maintain a constant voltage level despite variations in load. Tenthly, inspect for loose connections. Loose connections can increase resistance and cause voltage drop. Furthermore, understanding the difference between grounded and ungrounded conductors is important. Grounded conductors, typically identified by a white or grey insulation, are connected to the earth at the service entrance. Ungrounded conductors, typically identified by black, red, or blue insulation, carry the electrical current to the load. Grounding provides a low impedance path for fault currents to return to the source, which helps to protect against electrical shock and equipment damage. Ungrounded conductors are energized and should be handled with caution. The NEC specifies requirements for grounding and bonding to ensure electrical safety. Firstly, the grounded conductor is connected to the earth at the service entrance. Secondly, the grounding electrode system must be installed in accordance with NEC requirements. Thirdly, all metal enclosures and equipment must be bonded together to create a low impedance path for fault currents. Fourthly, ground fault circuit interrupters, or GFCIs, are required in certain locations to protect against electrical shock. Fifthly, arc fault circuit interrupters, or SIs, are required in certain locations to protect against arc faults, which can cause fires. Sixthly, surge protective devices, or SPDs, can protect against voltage surges caused by lightning or other events. Seventhly, equipment grounding conductors, or EGs, are used to connect metal enclosures and equipment to the grounding system. Eighthly, bonding jumpers are used to connect different parts of the grounding system together. Ninthly, the size of grounding conductors must be determined in accordance with NEC requirements. Tenthly, the installation of grounding systems must be inspected and tested to ensure proper performance. Moreover, knowing about overcurrent protection devices is also essential. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. Overloads occur when the current in a circuit exceeds its rated capacity, while short circuits occur when there is a low resistance path between two conductors. Overcurrent protection devices interrupt the flow of current when an overcurrent condition is detected, preventing damage to equipment and reducing the risk of fire. The NEC specifies requirements for overcurrent protection to ensure electrical safety. Firstly, circuit breakers and fuses must be properly sized to protect the conductors and equipment they serve. Secondly, circuit breakers must be listed and labeled for the intended application. Thirdly, fuses must be of the correct type and rating for the circuit. Fourthly, overcurrent protection devices must be readily accessible. Fifthly, overcurrent protection devices must be installed in enclosures that provide adequate protection. Sixthly, branch circuits must be protected by overcurrent devices rated no higher than the ampacity of the conductors. Seventhly, feeder circuits must be protected by overcurrent devices rated no higher than the ampacity of the conductors. Eighthly, motor circuits must be protected by overcurrent devices that are sized to allow for the motor's starting current. Ninthly, transformer circuits must be protected by overcurrent devices that are sized to protect the transformer from overloads. Tenthly, the installation of overcurrent protection devices must be inspected and tested to ensure proper performance. Let's delve into specific scenarios where either FMC or MC cable might be preferred. Imagine wiring a lighting fixture in a suspended ceiling. FMC could be a suitable option for the final connection from the junction box to the fixture, providing flexibility for adjustments and easy installation. However, for longer runs within the ceiling, MC cable might be preferred due to its inherent mechanical protection and lack of length restrictions, ensuring a more robust and reliable installation. Consider also wiring a motor in an industrial setting. While FMC might be used for short connections to the motor, MC cable would be a more robust choice for the main feeder, protecting the conductors from potential physical damage in the demanding industrial environment. For residential wiring, MC cable is often used extensively due to its ease of installation, inherent protection, and suitability for running through walls and ceilings. However, in certain applications, such as connected appliances, FMC may be used for short, flexible connections. Another consideration is the cost. FMC is typically less expensive than MC cable, making it an attractive option for short runs where flexibility is required and mechanical protection is less critical. However, for longer runs, the cost difference may be offset by the labor savings associated with installing MC cable, which requires fewer supports and offers greater protection. Ultimately, the choice between FMC and MC cable depends on a careful evaluation of the specific application requirements, taking into account factors such as flexibility, mechanical protection, length of run, environmental conditions, and cost. Consulting with a qualified electrician and adhering to all applicable electrical codes is essential to ensure a safe and reliable installation. By understanding the differences in mechanical properties and code requirements, one can make informed decisions about when to use FMC versus MC cable in various electrical installations. Remember to always prioritize safety and consult with qualified professionals when working with electricity. Always de-energize circuits before working on them and follow all applicable safety procedures.